Last video, we started looking at neutralization reactions, right? We said that when you have an acid and it reacts with a base, we get water and then a salt, and that the pH of a neutralization reaction is not always neutral. So I do want to do a quick review of that. So our first one was if we had a strong acid. I'm just going to use SA for strong acid, and then a strong base, so SB. So strong acid, strong base neutralization reaction. So I'm just going to use HA as our generic acid. I'm going to use MOH as a generic base, M standing for some sort of metal. I am going to get water plus my salt, so the cation from my base and then the anion from my acid, and then generally that salt is soluble in aqueous solution. A specific example, if I use hydrochloric acid, right, a strong acid, sodium hydroxide, a strong base, I'm getting water, right? It's the hydrogen ion from that acid reacting with the hydroxide ion from that base. I do have a covalent bond between them, right? Sometimes I'll write it as HOH because it helps us balance them, but do note that those bonds are covalent. So it's not actually a hydrogen ion and a hydroxide ion. We're actually forming our covalent molecule water, right? It's bent, 2 lone pairs on there, if you remember back to your general chemistry 1 days. And then my salt is sodium chloride. And then I do want us to be able to just write our net ionic equations from this. So remember, a strong acid is always going to be completely dissociated, right? That's our definition of a strong acid. It's always completely ionized. That would be the better way to say it. And you can write H+, but hydronium ions is the better way to write it. Protons in water do attach themselves to water, so you don't generally have free protons floating around in water. So I like to write it as hydronium ions and chloride. I have sodium and hydroxide ions, and we know that the conjugate, right, the anion from a strong acid is inert. It's not going to react with water to produce hydroxide ions. The cation from my strong base is also inert, so when I write my ionic equation, I can cross those out, or my net ionic equation. If I go back over to this side, right, if I want to think about it in terms of spectator ions, because this is completely dissociated and this is a soluble salt using our solubility rules, I do have chloride on both sides, right? It's inert. And I also have sodium on both sides. Remember, ions that are exactly the same on both sides of our chemical equation, our spectator ions are not participating, right? They're not undergoing a chemical change, so we can just cross them right out. So if I was to write my net ionic equation for this, I'm going to have hydronium ions plus hydroxide ions, and then that's going to water. And then I do need a 2 here to balance it because I'm using hydronium versus just the proton. I do need to have that 2 there. Because my products are only water, right, my pH is going to be equal to 7. Right? This is essentially the opposite reaction of my ionization of water, right? If we were to write our reaction for Kw, it's water plus water going to hydroxide plus hydronium. If these are present in equal amounts, right, if I was to write my equilibrium constant expression, it's just going to be these. I'm not going to include water. Since it's a 1-to-1 relationship, my pH is going to be 7. If I was to look at a weak base, actually, sorry, let's do weak acid first. So WA for weak acid, and then strong base, so SB, neutralization reaction. This time the weak acid is largely undissociated. And we ionized, I guess would be the better way to say that, largely unionized. I'm not sure if that's a word. It is now. It is not ionized. So our net ionic equation is going to involve proton transfer from our weak acid HA to that strong base. So essentially, I'm going to have HA, right, my weak acid, I'm going to keep it together, right? Instead of writing them as hydronium and then an anion and crossing out that anion, because it's largely unionized, I am going to keep those together. Just fixing my handwriting here a little bit so you can read what I'm saying. And then because I'm using a strong base, it is going to be completely dissociated. So I am just going to write it as hydroxide. I'm just going right to my net ionic equation here. I'm going to get water plus my conjugate base, right? My anion from my acid. And we had said at the beginning of chapter 14, right? The anion from a weak acid is basic. So this will react with water to produce hydroxide ions, and our pH is going to be greater than 7.00. Right? If we were to do an example, I could use acetic acid. Oop, forgot a carbon here, CH3CO2. Sorry, I'm all over the place here. And potassium hydroxide for something different. We're going to get water plus potassium acetate. Acetate was one of those polyatomic ions that you needed to memorize in General Chemistry 1. And then again, going right to my net ionic equation, right? Potassium hydroxide is completely dissociated. Using my solubility rules, this is also completely dissociated in aqueous solution. Potassium ions are inert, so I'm not going to include them. So my net ionic equation is my acid, HA. In this case, we're using acetate to represent A, plus hydroxide, going to water, plus acetate ions, right? My conjugate base, right? Acetate is the conjugate base of that acid. And then, like I said, this is basic, right? It will react with water. So I could write my base dissociation equilibrium equation for that, right? Acetate ions are going to react with water. This is from last week. I'm going to produce hydroxide ions plus my conjugate acid, right? Because I'm producing hydroxide, I'm going to have a basic pH. So if we have a strong acid, strong base neutralization reaction, right? My salt is inert. Both of these are spectator ions. Neither one is going to react with water to produce hydronium or hydroxide. All I have is water then, so I have a neutral pH. When I have a weak acid, strong base, right? My weak acid is largely unionized. So when I write my equation, right, I'm going to keep it together, keep it as HA. My strong base is completely dissociated, right? Definition of my strong base. My salt is soluble. Potassium is inert, so we can just get rid of it. It's not reactive, so we're not going to include it in my net ionic equation. And then my conjugate base here is actually basic, right? This is this. It reacts with water to produce hydroxide, giving me a basic pH. Our third scenario is if we had a strong acid, weak base. So SA for strong acid again, WB for weak base. And then this time our net ionic equation is going to involve proton transfer from the strong acid, which we're going to write as hydronium ions, to our weak base. So kind of our generic version. My strong acid is going to be completely ionized, right? Again, that's the definition of our strong acid. So instead of writing it as HA, it's H3O plus and A minus. Remember A minus, right? The anion from my strong acid in this case is inert. So if I had HBr, I don't care about the Br minus. It's the hydrogen ion that attaches itself to water to form hydronium ions that we're going to care about. It's going to react with my base. I'm just going to use B for my base. Again, we're going to get water plus my conjugate acid, which I'm going to write as BH plus. So we're taking a proton from hydronium, right? We're giving it to my base. So we added H plus to this, making it my conjugate acid. This lost a proton to form water, which is my conjugate base in this case. If we were to use a real example, let's use HBr since we just mentioned it, plus let's use Cn minus as my base. I know that this is going to be completely dissociated by this, sorry, I mean my acid, right? H plus and Br minus, again, I'm going to write it as H3O plus. I know that my Br minus is not going to react with water, right? It is inert. So I'm going to end up with a net ionic equation of H3O plus Cn minus. My hydronium ions is going to lose a proton, so only 2 of them here. And I get HCN. So aqueous, 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 right? This is acidic. It will react with water. We'll write that equation here in a minute. So my pH is going to be acidic, so it's going to be less than 7, right? Just like we did up here, this was basic, so it's going to react with water. This is acidic, it will also react with water, so we're going to write our acid dissociation equilibrium equation. We're going to produce hydronium ions, right? My acid here is going to lose a proton. It's going to give it to water to form hydronium. I'm going to end up with my conjugate base. So again, because I'm forming hydronium, I am going to have an acidic solution. So going back up, here I just have water. Let's see, we're all looking at the same thing here. For this one, I actually have an anion that is basic. For this one, I don't really have the generic version written out all the way, but we'll circle this one here for us. Right, I end up with my conjugate acid being acidic. We could add that up here just for consistency. Acidic, pH less than 7. And then one other scenario, that is if I have a weak acid, weak base. And we had said in the video that my pH for this one really just does depend on the acidic, whether, right, the Ka and the Kb. So whether the acid that I'm forming is stronger than the base, or if the base is stronger than the acid, or if they're equal. So an example for this one, if I was to take HA, add it to B, I am forming water. I just have to write my acid like with the hydronium ions. Actually, it might be easier to understand if we actually do a real example. So if I was to take HF and react it with ammonia. I am getting F minus, right? That loses a proton, plus NH4 plus. So it's written kind of weird, but this is my salt, right? If I was to put it the way we normally would see a salt, right? Cation first, and then anion second. It's just using our solubility rules. It is completely dissociated. So I would completely separate it like that. And then I'm not seeing water when I write it this way, but remember my weak acid is partially dissociated. So I do have some H3O plus and some F minus. Most of it is in this form, but some of it is H3O plus. You can think about this as giving the proton, the arrow should go here, giving the proton to ammonia to form ammonium, and then that would leave water. The other way you can think about it is these are all aqueous. They are all in solution with water. So even though I'm not writing water when I write this equation, I do have water. And then as far as acid-base properties go, this thing is basic. This one is acidic. So my fluoride ions will react with water to produce hydroxide ions and its conjugate acid HF. Ammonium will react with water to form hydronium ions and its conjugate base NH3 ammonia. So these acid-base properties of a weak acid, weak base solution just depends which one of these is stronger. I would compare the Ka to my acid to the Kb for my base. Remember, the larger the equilibrium constant, the more, the stronger the dissociation. So if it's a bigger Ka, it's a stronger acid. If it's a bigger Kb, it's a stronger base. If they're the same, if the Kb for this is the same as the Ka for this, then it's actually going to be a neutral solution. If the Kb is stronger than the Ka, basic. If the Ka is stronger than the Kb, acidic. So this one you do have to take kind of on a case-by-case basis, depending on what acid and base you're starting out with. So I want to do a couple examples like we did in the previous video where I give us some salts and then we have to determine if that salt is going to be neutral, acidic, or basic. So if we go back up to this one, right, my salt would be ammonium fluoride. Given that, are you going to have an acidic, basic, neutral solution, or do you need more information, right? In this case, I would actually need to know the Ka and the Kb to be able to compare them. So a couple of examples for us. KBr, I'm just going to list them here. Sodium nitrite, ammonium bromide, zinc chloride, and then ammonium fluoride. So just like we did in the previous video, if you could pause and then determine if the salt solution is going to be acidic, basic, or neutral on your own. And then after you've done that, hit play again and we can go over those results. All right, hopefully you guys had some success on that. So the first step might be to just split them into ions. So I do have potassium ions and then bromide. Potassium ions are group 1A cations. Those are always going to be inert. Those are never going to react with water to produce hydroxide ions or hydronium ions. And then bromide is the conjugate base of a strong acid, HBr, and we know that those are also inert. So neither my cation or my anion will react with water to produce hydroxide ions or hydronium ions. So this is going to be a neutral salt. My pH, if I have KBr in water, is going to be 7. Sodium nitrite, again, breaking them into ions. I have sodium ions and then nitrite ions. Again, I have a group 1A cation that is always going to be inert. It's not going to react with water, so we can ignore that. Nitrite here, however, is the conjugate of a weak acid, right? NH2 is a weak acid. NH3 is a strong acid. Be careful not to get those two mixed up, right? Nitrate ions versus nitrite ions. Nitrate ions, NH3 minus, are going to be inert. NH2, however, NH2 minus, this is going to be basic. So if I have sodium nitrite, I expect a basic pH, right? NH2 minus will react with water. I'm writing my base dissociation equilibrium equation here to produce hydroxide plus the conjugate acid. Ammonium bromide, NH4 plus, Br minus. Again, bromide ions, those come from HBr, which is a strong acid. So those are not going to react with water. My ammonium ions, however, are acidic, or is acidic. It's a weak acid. So this time my salt is going to be acidic, right? If I had ammonium bromide in water, the pH of that solution is going to be less than 7. If I have sodium nitrate in water, the pH of that solution is actually going to be greater than 7. I'm just going to space these out a little bit because I'm running out of room to write. So zinc, it's a fixed charge of 2+, and then chloride, I happen to have 2 of them, but 1 or 2, they still come from HCl, right? Hydrogen chloride, hydrochloric acid is a strong acid. We know that Cl- is not going to react with water, so I can ignore it. And then zinc was one of those small, highly charged cations. So this is going to be an acidic solution. We talked about that at the very end of the previous video. So this is going to be an acidic solution. And then this one we actually just did. So I gave us the same salt as up here. I have ammonium ions and I have fluoride ions. This one is acidic. This one is basic. So we could look up Ka and Kb's to actually be able to answer the question. Since I didn't give them to us, we can just say we need the Ka and Kb to determine, right? It could be neutral. If the Ka is equal to the Kb, it could be acidic or it could be basic, just depending on those relative values. In our next video, we will actually go through an example where we calculate the pH instead of just predicting the pH.